What's up, everybody? This is Coach Sharp. Welcome back to my advanced algebra / algebra 2 notes videos. Today we are in the newly redesigned Unit 2, which is the exponential and log unit, which is the old Unit 5. We are doing our ILP on exponential functions, which is, or should be, let me say that, should be a review of pretty much what y'all did in the entire exponential function unit in Algebra 1. So it's just refreshing and building on that as we prepare to add new stuff on top of it. So let me go ahead and get started. My pad is upside down. That would help. There we go. All right, so we are in the packet for this lesson. Again, y'all had not received this. So we did it in our notebooks. So if you're trying to get caught up, you need to do the same thing. I would put, let's see if I can actually make a circle here. I would put investigating exponential functions at the top of your paper. You can put diagnostic activity on like the first line of your paper. And if you want to put bacteria in the swimming pool on the second line of your paper, you can. You don't necessarily have to. You could just go ahead and start with number 1. Okay. The bacteria count in a heated swimming pool is 1,500 bacteria per cubic centimeter on Monday morning at 8 a.m. The count doubles each day thereafter. What bacteria count can you expect on Wednesday at 8 a.m.? Give an estimate that's too low, one that's too high, and one that's just right. So you can write number 1. Again, you don't have to write any of this or all of this. You can just simply put too low, an estimate that would be too low, too high, one that would be too high, and one you think is just right. So based on the information that's given to us, Monday morning, 8 a.m., what's the count we can expect Wednesday morning, 8 a.m.? That's 2 days later. The count doubles each day. So we're starting with 1,500. So it would double to 3,000 Tuesday morning at 8 a.m. and then double to 6,000 Wednesday morning at 8 a.m. So just right estimate would be about 6,000, and then too low, too high can be anything below or above that. Don't put 5,999 and 6,001, but you could put, 2,500 and 10,000. Some people said some bigger numbers even than that in class. But you need to put a too low estimate and a too high estimate as well. All right. So then for number 2, you're going to complete this table. Again, you don't necessarily have to draw the whole table. Just you can kind of make 2 rows, or two rows more or less. First row, you can just put days. I mean, don't put in parentheses like that. Do days. And then number of bacteria. I mean, you could just even cross out number of and put bacteria. Then you just do this on like two lines in a row. If you want to draw the vertical lines kind of in between, y'all can do that. But day 0 is Monday at 8 a.m. So that was 1,500. So after 1 day is going to be 3,000. 2 days is going to be 6,000. So you got to double it for the next few days after that. Again, we're just multiplying by 2. I think y'all can fill that in on your own. Okay. I'm going to give y'all a minute to do that, trusting that y'all actually will, because I'm still going to have to write some of these numbers in, I guess. But I'm going to give y'all a minute to do that because I do actually got to go grab something I forgot off camera. So y'all do that real quick. I'll go grab it. Oh, I did that. All right. So hopefully you had time to fill in that table. If you just kept doubling, you would have gotten 12,000. So I'm going to put 12K to shorthand it. So I don't got to fit all those zeros in there. 24,000 and then 48,000. All right. So just to give you all an idea of this, I have no clue how true to a real life example this might be, but again, we're pretending, we shut the pool off September 30th or whenever you want to shut it off for the winter. You don't mind, not using chlorine or any of the chemicals for a couple weeks just to shut it down, and then you can start treating it again. Again, if you don't have one or don't know anybody who owns a pool, you gotta treat it with chlorine and other chemicals to keep the bacteria and the algae and all that stuff from growing in it like it might in a lake or whatever. Another fresh body. So the salt water kind of the salt water, the salinity in that kind of helps, with the bacteria in that. Although again, I wouldn't, mainly because of salt water, I wouldn't necessarily drink ocean water either. But anyway, so number of bacteria per cubic centimeter. We're at 5 days. If you counted it out, day 0 is Monday. So day 5 would be Saturday at 8 a.m. All right. What I want to grab regular glue stick and the lid. Again, if you were in class when I did this, you saw the example. This lid, I don't know how clear of a perspective y'all are getting with my video in the corner, but this lid is 2 cubic centimeters, roughly. So half of this lid would be 48,000 bacteria, or if you just doubled it, it'd be 96,000 bacteria in that lid. Okay. So to put it in perspective, again, you might not have quite the perspective on it, seeing it in the little corner of the video box, but I'll hold it up if y'all can see it. I mean, it's not even really as big as the kind of the top part of my thumb. It's roughly that, I guess, not slightly smaller than that. So we kind of estimated in class. So we're talking about bacteria in a pool, and I was trying to come up with comparison on, in-ground or above ground pool like y'all might have in your backyard. But then I said, just let me scale this out and kind of make it gross. So I pulled up, I'm not going to go pull it up now so y'all can see it, but I pulled up the competition swimming pool at UGA, University of Georgia. It's an Olympic size swimming pool. They've hosted SEC championships there. They've hosted the NCAA national championships there. So it's legit competition size swimming pool. The numbers I looked up said it can hold 844,000 gallons of water. All right. It's 96,000 bacteria in this cap. We came to the number in class. I don't know if this is right. I don't have 300 of these to try to fill up a milk jug, but I could have looked up volume wise milk jug and this and try to figure out, I guess, but we said roughly 300 of these in a gallon jug of milk. So 96,000 times 300, which is 28,800,000 bacteria in 1 gallon of water. 28,800,000 times 844,000 gallons of water. So you're looking at trillions and trillions of bacteria, which is gross. All right. Number 3, suppose we want to know the expected bacteria count at 2 p.m. Thursday, 3.25 days after the initial count. Use the values in your table to estimate the number of bacteria. Explain your thinking. So I would just kind of isolate this. So we said this is Monday, this is Tuesday, Wednesday, Thursday, Friday. And we said that was Saturday. But so don't need that for this problem. 2 p.m. Thursday. So this day 3, it's 12,000 bacteria. Thursday, it's 8 a.m. Thursday. So 2 p.m. is going to be between Thursday and Friday, between 12 and 24,000. 2 p.m., which is 6 hours after 8 a.m. 6 hours is a quarter of 24 hours. That's why it's 3.25 days. So quick estimate for me, if I just look at that 24 hours in a box, we start with 12,000, we go up 24,000. So we increase by 12K overall. A quarter of that is 3K. So I would then take my 3K, add it to the original 12K, and I would get 15,000. I'm actually going to write 15,000, not 15K. 15,000. The bacteria go up. I will put 12K here. 12K from Thursday to Friday. 25% is 3K. We add it to the original original 12K and get my 15K. So that's what y'all can write for number 3. I'm going to go ahead and move on. So if you need to pause it real quick so you can write it down. All right. Number 4. To answer this question more precisely, it would be helpful if we can write a function for the bacteria count. Okay. There's a lot you can read there. I read it in class, but basically we're trying to find a pattern. Okay. So it's ask, what do we do on day 1? Okay. Day 1, we started with 1,500 bacteria, doubled it. So how do you get the number of bacteria after 1 day? We got 3,000, which is 1,500 times 2. Started with our 1,500 bacteria, doubled it. Then after 2 days, we doubled what we had after 1 day. After 1 day was 1,500 times 2. And then we doubled that, multiplied it by 2 again. Then after 3 days, we doubled what we had after 2 days. So all of this now, 1,500 times 2 times 2, and doubled it again. Okay. So what stays the same? 1,500 stays the same. What is changing? The number of times we multiply by 2 changes. Okay. So that's what you can write for number 4. Again, pause it if you need to real quick, but I already made this video longer than I wanted to at this point, so I'm just moving right along. All right. 5, use the pattern from problem 3 to write a function P that represents the number of bacteria after 2 days. All right, so to write a function, I learned about functions in Algebra 1. Function could be a letter, it could be f of x. It's just what's going to be on one side of your equal sign, and then everything else is on the other. So for all of those, if we scrolled back up, we know we have 1,500. 1,500 times 2, 1,500 times 2 times 2, 1,500 times 2 times 2 times 2. So I know I'm going to start with 1,500. And in all of those, I'm multiplying by 2, but the number of times that I'm multiplying by 2 is changing. So I got to be able to express that. I have to have a t in here representing my number of days, and I have to express how many times I multiply by 2, how that changes per day. So if you go back up and scroll up, we almost are going to work backwards, okay? So after day 3, if we look, we have 1,500 times 2 times 2 times 2. So after day 3, I'm multiplying by 2 3 times. After day 2, 1,500 times 2 times 2, I'm multiplying by 2 twice. And then day 1, I'm only multiplying by 2 1 time. So if we take that into consideration, day 3, I've got 2 times 2 times 2. What's another way to write that? 2 cubed. Day 2, I've got 2 times 2. What's another way to write that? 2 squared. Day 1, I only have 1, 2 that I'm multiplying by, but a way to write that in a form that's equivalent to that would be 2 to the first power. Anything to the first power is itself. So day 1, 2 to the first. Day 2, 2 squared. Day 3, day cubed. Day cubed, 2 cubed. Excuse me. So whatever day it is, that's going to be our exponent. So what's the function that's going to give us our bacteria after T days? I'm going to put the 2 up here as my exponent. So 1,500 times 2 to the T power. How can you use the function to determine, again, pause this if you need to write it. You don't necessarily have to write this stuff over here if you already started to. My apologies. But this is really all you need. All right. So how can we use the function to determine the number of bacteria present? Well, all we're going to do is plug in. I'm going to leave it up here so y'all can see it. Plug in the number of days for T. So it says number of bacteria after T days. It tells us 3.25 days. So I'm just going to plug it in, which is going to give me 1,500 times 2 to the 3.25 power. Now, punching in our calculator. So this is different from previously when we had to use e to the x power, all right? So just straight up got 1,500. I know it's backwards. 1,500 times, I'm going to do 2. There's my 2. And then I got to hit my exponent button, which is dcx squared. dcx squared on the side, x squared by my pinky. Above that, that arrow looking thing between x squared and pi. Again, that's what we call the caret. That's what I'm going to hit, which gives me that, which means that's my exponent now. Now I can punch in 3.25. Hit equals. I'll flash it up here just in case you want to pause it and can see it. I mean, it's backwards, but that's 14,570. Excuse me, not 570, 270. 14,270.49. All right. So that's bacteria. A couple things to note here. I left bacteria as a decimal. Again, bacteria is a living thing. So to me, I would just go ahead and round up to the next whole living thing, if you will. So 14,271. Think about when you're doing a human population count. If you have a fraction of a human, you're not going to say that there's 12,792.63 residents of Covington. You would round up to the next whole number. I didn't forget what I said. It's 12,000 something. To round up to the next whole number. So that's kind of my thought process here. So I would personally say 14,271. If you wanted to keep the decimal, that's fine. When y'all are filling in your worksheet, even with this, if you knew you had to round by the traditional rounding rules, y'all know I would not round up to 71. I would just keep it 70. I'm a little more flexible, specifically when it comes to bacteria. But if we're talking about money's got 2 decimal spots for cents, so we can be precise with that. And then population, like I said, you're not gonna have, in this case, if this were humans, 49% of humans. So, if we're talking about humans, I would definitely round up, but a little more leeway with this one, I guess. All right. The other thing, we estimated 15,000. It's a little bit under that. So without going too in detail, because we got to move on and getting on Desmos to show y'all, I'll just kind of do it over here in the margin real quick. When we made that estimate of 15,000, we were basically treating it like a linear line going up from 12,000 to 24,000, and we hit whatever spot on the line. When in reality, we know it's exponential growth. We know it's exponential growth, so we're really going to have a curve like that. So it's not quite this exaggerated. Let me redo that so y'all get a little better idea, I guess. It's not quite that exaggerated, but it's still going to be something like that. So it's going to bow out a little more. So it will be lower. So if this is 15,000, if we have a y-axis over here, if that's 15,000, that's a little bit above 14,000. So it makes sense. All right. I'm going to clear this out. Again, pause it if you still need it. So use graphing technology to graph the function, sketch the graph. How did I just zoom in? I didn't mean to zoom in. All right. I've got to, I think I had y'all. Did I have y'all sketch it? I think I had y'all sketch it. I'll just throw something up real quick. So when you're sketching a graph, you could do more traditionally the two axes that cross to kind of give you the four quadrants, but if we actually looked at this graph on Desmos, it would leak out here into the second quadrant like this and start to flatten out at the x-axis, but I'm not concerned with that portion of it, so we can just leave this as is. So we're gonna have 1 day, 2 day, 3 day, 4 day, 5 day. I'll mark it since I got it, but I'm gonna count by 5,000. So 5,000, 10,000, 15, 20, 25, 30, 35, 40, 45. We'll go to 50. Okay. So 0 days, we had 1,500 bacteria. All right. Just okay. Very Christmas coloring. I'm just gonna do this far because we only went to 32. So, or no, we went to 40. I'm sorry. One more thing. All right, so 0, 1,500, 1, 3,000, 2, 6,000, 3, 12,000. 6, 7, 8. That was kind of sloppy. 4, 24,000. 5, 48,000, which is almost all the way up here. So y'all really can see it there at the end where you start to get, make a bold line. This curve going up. Okay. Yeah, pause it if y'all need to stop so y'all can sketch that. All right. If nothing's done, the bacteria will continue to double. How long will it take for the count to reach 3 million bacteria? Write an equation to represent this situation. Find at least 2 different ways to solve the equation. Well, again, for the sake of time, I'll show y'all some of the algebra here for way 1, and then way 2 would be looking at the graph. I'm not gonna pull it up for the sake of time because I didn't already have it pulled up. Which again, that one's probably on me, but just for the sake of time, well, you're just gonna take my word for it. So we're now saying 1,500. We're saying 1,500 times 2 to the t power. Again, so when we have this, we could plug in any number of days and calculate the bacteria that we would get. But now I know I'm trying to aim for specifically 3 million bacteria. So I got to try to solve for t. So whatever value of t would give me this. Okay. Algebraically, there's one step I could do from here. It would be to divide by 1,500. So 3 million divided by 1,500 is 2,000 equals 2 to the t power. And now from here, I would actually have to use a logarithm. Okay. You don't have to write what I'm about to put in black. but you'd have to use a logarithm. This would turn into log base 2 of 2000 equals t. Now you've got it set equal to t, and you could solve for t. We'll get into that more later. But the other thing to do would be to, if you had actually typed in this equation, 1500 times 2 to the, you would actually have to put 2 to the x into the Desmos calculator. 1500 times 2 to the x power. And then if you follow the curve, you would see it finally cross 3 million at like 10.996. Is it 996 or 966? I want to say 966. I don't think it was 996. Days, it was 10.9966, and then you had like 3,440. Well, I don't think it was 444, but like 442,000, something like that. 440 something. So 10.966 days, which, I mean, you can basically round up to 11 days. Okay. For all intents and purposes, we will round that up to 11 days. All right. Clear this out. All right. Again, that honestly took a little longer than I wanted to, so I'm going to stop this video. And then we'll talk about the engage and explore sections separately. So I've at least got the diagnostic on there now. Again, if y'all didn't get it, y'all can go ahead and put it in your notes for y'all to turn in, and I'll see when I get the other video up. I'll get the other video up when I can. So until then, I'll see you guys in class.